Okay, folks, in this video I want to do a quick recap of some of the highlights of finding the domains or dealing with the domains of a function. Just go ahead and read the caveat here. I'm not going to be able to cover everything about the idea of domain. In fact, I'm not even going to choose to define it in this video, but I just want to review a few things that you've seen before and hopefully put you on the right track for going forward with more complicated domain questions. So notice that in number 2 here, I've listed 4 functions. We've got f of x, g of x, h of x, k of x. And notice that all 4 of these functions have the same explicit rule for what you're supposed to do to an input value. Okay. In all cases, whenever you take an input value, what are you supposed to do with it? You're supposed to square it, and that will give you the resulting output. This is the x squared function. Okay, but for each one of these, I've specified a different domain, and you can take a look at these. So let's go ahead and graph these functions just so we can see. If we were to graph the first function, f of x equals x squared, that's this this general quadratic shape of a function, but we only want to do it for input values that are either 0 or positive. Well, the graph of that function would look something like this. Okay. Notice that because, and this is going back to interval notation, you might be a little rusty on this, because this is a bracket here, we go ahead and make sure that means that we include the value 0. If this were parentheses, then we would exclude the value 0, but we would include everything that came just immediately after 0. So we can kind of get the contrast here when we look at the second graph. Here we're asked to graph g of x. Again, it's the x squared function, but now we want to do it on the interval from minus infinity to 0. And, well, the graph of this function would look something like this. And I didn't quite get that. Let me clean that up just a little bit. Let's try that again. Let's try that one more time. In fact, I'm just going to write it this way. I'm going to go ahead and put the open dot here and graph this. Okay. This isn't a great looking parabola. I apologize for that. But the idea here is that I'm only graphing the left side, the left half, I guess, if you will, of this parabola. And specifically, I want to point out that I'm only plugging in negative values in the domain. For instance, if I were to plug in -3 into the function, it would spit out a +9, giving us the ordered pair here. This would be the ordered pair -3, +9. And I'm doing that for all negative numbers, not just the numbers that I've listed here, but all negative numbers on the real number line. And what am I not including? Specifically, it's very important that I'm not including the value 0 here. So you can see that that was represented in the domain by the fact that this was a parentheses here, and we see that represented in the graph by putting an open dot there. That means that all values immediately to the left of 0 are included, but 0 itself is excluded. That's what we mean mathematically when we denote an open dot on a graph like that. So let's go ahead and look at letter h now. Letter h, again, we're dealing with the x squared function. Again, it's this parabola that looks something like this. Okay? But we want to only take values between -3 and 1. Okay? Well, -3 is not actually included in the domain. How do I know that? I've explicitly said that by giving a parenthesis here. -3 is not included in the domain, but let's just suppose it were. If it were included in the domain, what would the resulting output value be? Well, if I take h of -3, that's equal to -3 squared, which is equal to 9. So that would give us the ordered pair -3, 9. But what I'm going to do is, rather than plotting a point there, I'm going to plot the hole. That hole is at the ordered pair -3, 9. Okay, let's tackle the other endpoint. So the rightmost endpoint of this particular domain is when x equals 1. Okay. Notice that 1 is included in the domain. How do I know that? Because we've gone ahead and put a bracket there as opposed to the parentheses, meaning that -3 was excluded, but 1 here has the bracket, so it is included. If I were to plug 1 into the function, well, what would h of 1 be? I know we can all do this, but let's just practice. 1 squared, that gives us 1, so we've got the ordered pair 1, 1, and that is included in the domain. Okay, because I have the graph of x squared memorized, I can go ahead and just finish filling it in the picture. Maybe I would need to plot other points if this were a more complicated function, but I think I'm okay to go ahead and graph this. Let's see how I can do on this machine. So this would look something, come on, something like this, rising up to there. Okay, for some reason I'm having a little bit of trouble drawing on my screen today. But that's basically what we're talking about. It's the parabola, and this part's not actually graphed, but the parabola continues on like this. But what have we included in the graph? Just this portion right here, which corresponds to the x values between, let me do that in a different color, which corresponds to the x values between -3 and 1. So one way to look at this is all of these x values right here are the domain of the graph function. So each corresponding point that is shaded blue here has a or each x value that's shaded blue here has a corresponding point on the function. Okay. So the last one we have to do is the function k of x is equal to x squared, and this is kind of what I want to hone in on today. So in this case, I did not specify what the domain of this function was. And going forward, we're just going to take it as a matter of convention. When we don't specify what the domain of a function is, we take it to be the largest set of real numbers for which the function is defined. In fact, we can go ahead and say that right here in point number 3. When the domain of a function is not explicitly given, it is understood to be the largest set of real numbers for which the operations of the function are defined. Okay. Well, if we go back to this function, this is the x squared function, I can square all real numbers. So since I can square all real numbers, that means that the domain of this function is all. So because the domain of this function is all real numbers, then when I ask you to just graph its function, it's understood that the domain is all real numbers, and here we have the graph of this function. Okay, so let's move on to the next page, and this kind of gets to the heart of what we're doing in this domain review. Certainly lots of operations are only defined for certain numbers, but there are 3 major problematic operations that are at the heart of most domain questions that we encounter in this class. The first problematic operation is division. And specifically, I want to say that we can divide by all real numbers except for 0. So division is defined. So in fact, let's go ahead and give the, we can divide by all real numbers except for 0. Okay. So where this comes into play most often is we need to make sure that when we're defining a function's domain, we need to, if it has fractions, if the function has fractions in it, we need to exclude any values that would result in a 0 in the denominator. So let's just say that, exclude any values that would result in a 0 in denominators. Okay. So for example, we have this function here, f of x is equal to x plus 2 over x minus 2. So if I want to give the domain of this function, what I'm going to do is I'm going to prohibit the denominator of the function from being 0. So we need x minus 2 to not equal 0. So what did I do? I took the denominator of this function, x minus 2, and I said that it could not equal 0. And you don't, there's lots of ways you could denote this. I mean, this is just sort of your own scratch work for determining what the domain is, but maybe you've never solved an equation with does not equal, but it's kind of the same idea. And we could say that x cannot equal then 2. Okay. So what is the domain of this function? Well, the domain is, I'm going to go ahead and give it in set builder notation, the set of numbers x such that x can be any real number and x cannot equal 2. So for those of you that are rusty with set builder notation, this is the open brace here that starts a set. Then I go ahead and just list the typical element. Okay, and then here I've said that x must be a real number. So remember this symbol looks sort of like an E here, stands for is an element of. So x must be an element of the real numbers, and x cannot equal 2. And then I go ahead and close the curly brace. Let me just erase that real quick. Okay. So that's the first problematic operation. So whenever you're dealing with a function that has division in it, you need to do some sort of version of saying, I need to ensure that the denominator of that function is not 0. Okay, the next problematic operation is that we can only take the even-powered roots of non-negative numbers. Okay, so another way to say that is we cannot take even-powered roots of negative numbers. That is, that operation is not defined in the real numbers when those numbers are negative. So, for example, the square root of -4 is undefined in the reals, and the fourth root of -16 is undefined in the reals. Okay. This holds for any even-powered root, fourth root, second root, square roots, sixth roots, etc. Okay. So let's look at example D here. Here we're asked to give the domain of this function g of x, which is equal to the square root of 3x minus 7. Okay. So a lot of times people might take one of these problems and they might just try to guess what the domain is, sort of through a guess and test technique to determine what they need to make sure x isn't, so that the radicand, the expression underneath the radical sign, doesn't come out to be negative. But here's a sophisticated way, the correct way of determining what the domain of this is. So for the square root, we want the radicand. Remember, that's the name of the expression inside the square root. We want this radicand to be greater than or equal to 0. Okay? So what are we going to do? We're going to take the radicand of this function, 3x minus 7, and we're going to set it to be greater than or equal to 0. Now we can go ahead and just solve this as we would any other inequality. So this gives us 3x minus 7. 3x must be greater than or equal to 7. Or that x must be greater than or equal to 7/3. So what's the domain of this function? The domain in set builder notation would be the set of x such that x must be any real number and x must be greater than or equal to 7/3. That's writing the domain in set builder notation. Or we could do it, maybe interval notation is preferred here. In interval notation, the domain would be from 7/3 to infinity. And because this is a greater than or equal to, I go ahead and use the bracket here. Okay. So just to recap, we're dealing with these three problematic operations that are going to show up throughout the course. The first one is division, and we need to recall that you cannot divide by 0. The second one is even-powered roots, and we need to recall that you cannot take the even-powered root of a negative number. And then the last one is logarithms. You cannot take the log. In fact, let's do this in the affirmative. You can only take the log of a positive number. Okay. And folks, as a reminder, this is just a quick review video. I'm not really going into the definition of logarithms. I'm not explaining why we can only take the log of a positive number. I'm just operating off of that fact. I will do a video that reviews logarithms later on. So you can only take the log of a positive number. You cannot take the log of 0. You cannot take the log of any negative number. So let's go ahead and look at example f then. Give the domain of this function h of x, which is the natural log of, this is all inside the natural log, x squared minus x minus 6. Okay. So obviously we want to make sure that what we plug in for x results in a positive value. So for example, I know that if I plugged in, say, 5 for x, okay, if I found h of 5, this would be take the natural log of 5 squared minus 5 minus 6, which is the natural log of, this would be 25 minus 11, which is 14, and I can take the natural log of 14, so 5 is in the domain of our function h. Okay, so 5 is certainly a number that will work. And what would be an example of a number that wouldn't work? Well, let's say we tried to take h of 1. Well, h of 1 would be the natural log of 1 squared minus 1 minus 6, which would be the same thing as the natural log of negative 6, but this is undefined because I cannot take the log of a negative number. So 1 is not in the domain, whereas 5 is. Well, how do we know exactly what the domain of this function is? So here's the way to go ahead and do this for your log functions. We want to make sure that whatever we plug into the function gives us a positive argument. We're going to call the expression inside the logarithm the argument of the logarithm. So we want the argument of the log to be greater than 0. And this is important here. Remember that for square roots, we wanted to make sure that what we were plugging in after simplification, the radicand came out to be greater than or equal to 0. But for the logarithm, we want the argument to be strictly greater than 0. Notice this has the or equal to, this one does not. Okay? So how do we do that? Well, let's go ahead and set x squared minus x minus 6 to be greater than 0, which gives us x, well, I'm going to go ahead and factor this to find the zeros of it. So this gives us x minus 3 times x plus 2 must be greater than 0. And now there's many ways I could go about trying to determine, what numbers do I need to plug in for x to ensure that the expression comes out to be positive. I want to use this method, and I would prefer you to do this method as well because it's going to be similar to a method that we use later on in this course. So I'm going to go ahead and make a number line. And on the number line, I'm going to put anywhere where this inequality comes out to be 0. Well, this inequality comes out to be 0 at x equals negative 2 and again at x equals 3. So these were the zeros of the inequality. Okay. Then what I'm going to do is I'm going to go ahead and take test points. I'm going to take a test point from each of the 3 regions. Notice by listing the 2 zeros here, I've created 3 regions on this number line. And I'm going to take a test point from each region. So let's take negative 3, let's take 0, and let's take 4. So all I did was pick numbers that were within each of these intervals. So now let's go ahead and plug the test point in to the inequality and determine the sign. Well, if I take negative 3 and plug it into this inequality, what would the sign be? Well, this would be negative 3 minus 3 times negative 3 plus 2. And if we simplify that, that would give us negative 6 times negative 1, which gives us a positive 6. So I'm not going to write a positive 6 here. Instead, I'm just going to put a big plus sign. Okay? And what I'm looking for is what is the sign when I pick a number from this interval right here and plug it into the inequality. And in this case, it comes out to be positively signed. Okay. Similarly, if I took 0 and plug it in here, well, this would give me negative 3 times 2. That would give me negative 6. But I'm not really concerned about what the output is, the actual number. I'm just concerned about its sign. And what I'm saying is no matter what number I pick between negative 2 and 3, when I input that number into this expression, I will go ahead and get a negative sign. Okay. Likewise, if I took 4 and plugged it in, well, this would give me a positive expression here. This would give me a positive expression here. The product of two positive expressions is again positive. So if I want to ensure that the argument is greater than 0, then I want to only pick values from within these intervals here. I'm trying to make a parentheses there. That should look like a parentheses. In these intervals here, or this interval over here, and that's based upon this little test point method that I used. And what I did was I put any places where the argument was either 0 or undefined, and then I looked at its sign by using this test point method. Okay, so now I'm ready to state the domain of f, or excuse me, I guess it's the domain of h, and the domain of h for this function would be from -infinity to -2, and here I'm just going to use interval notation, union from 3 to infinity, meaning if I pick any number from within this interval or any number from within this interval and plug it into the function, I will be able to determine the output of that function. It will be defined. So that gives me the domain of h. All right, this was a long video. I hope you found it helpful. Go ahead and take the quiz now.